Okay, welcome to this video in our course on process control and optimization. And now we want to talk about the model building procedure. And the model building procedure is important to have in mind so that you have a structured way to building a model. Because modeling itself is sometimes driven by iterations and ideas, and some people say it's more like an art in the end, but it's still good to have a clear idea of how to structure the development, and therefore we want to have a look into it. So the first step in the model building procedure is actually defining so-called balance volumes and the system boundaries. And system boundary specification. Okay. And these balance volumes and also the system boundary specification are important so that you understand, okay, what of my streams that come into the system go in, what goes out, and there are a lot of quantities you can actually kind of count. So like how many molecules of a certain species goes into the system, how much mass goes in, how much energy goes in, and also goes out. And this is like the basic step you have to do to define these interface streams actually, and also come up with equations that use actually this fact that there are these conserved quantities you can actually kind of count. And one balance volume within our system, an example would be the balance volume for the liquid in the system. So if we assume this reactor is filled with a liquid, then we might have an area here where we have a liquid fluid in the system. So this is my liquid phase. And then there might be also balance volume for the gas phase within the system. We will not take care about that very much afterwards, but in principle, if you have to consider the gas phase, you should have a look into this volume as well. So, and this is related to step 1, so therefore we list here 1. The next step in the modeling procedure then is to think about, okay, what are my characterizing variables in the system I need to account for? So what actually do I want to describe by my model? And what are the variables I need to come up with a model then to be able to also develop a control loop. So this is then the specification of the characterizing variables. So, and now if you think about the system and we think about a more simple case, let's say we want to have in this reactor a homogeneous reaction. We want to be capable to describe homogeneous reactions. Then we might want to look into the following variables. So I listed up here again. So this is for 2, and it's about characterizing variables. And there are, for the most part, three types. The first one are the states in the system. The second one are the inputs of my system. And the third one might be the outputs of my system. So if we look into our example system on the left side, the states are like describing in what state the system is. So what might that be? One state thing could be the level, so this could be high, could be low, a certain band. We could have different distributions of components in this of species in the system, and we could have different temperatures in the system. So these are, for the most part, the states you might find. So as an example, this is the level. These are the concentrations of different species, molar concentrations, and the temperature of my system. Then the second type of important characterizing variables are the inputs to my system, and these could be like these flows here. So if this is a very simple control loop and can be assumed to be almost ideally. So this would mean that we could say the volume flow in from fluid 1 is one input we could set from the outside, and this is also coming with a certain distribution of concentrations, and it's coming with a certain temperature. And the same is true for the second flow, fluid 2, and this would mean we have also V dot in 2, Ci into, and T in 2. And as an output, or as outputs of the system, we might have an example, this flow down here, so e.g. the V dot out. And we could also say, related to this output, again, we have these concentrations, Ci out, and also the temperature T out. So these are the characterizing variables of my system, and the next thing then I have to do is doing the balance equations. Like that. Okay, so that's then 3. Balance equations. And here we have different ones we can use. I already talked about conserved quantities, and these are related to that. So we could have a mass balance, because we can count what amount of mass goes into the system and goes out and out of the system. And this would be then an equation of the following form. For our liquid in the system, the change of the mass within the system, so the stored liquid mass, changes with the mass that flows in through the fluid 1 plus the mass that flows in through fluid 2 minus what is leaving down here, so m dot out. And if we let this equation stand there, there's clearly an assumption in the background, and this assumption is that there is no exchange between the gas phase and the liquid phase, so that we don't have any term which is considering how the mass flow goes out of this volume into the other phase in the end. Then a second example could be like component balances. And this could look like the following. We say we have the change of the amount of a species in the system. We say it's Ni, so species I, and the amount of the species is N. And this is changing again from what is flowing in, Ni in 1 plus Ni in 2 minus what goes out. This is again the flow out, so N dot I out. And then we might have some kind of reactions within the system that change the amount of species I as well. So it's not like it's just flowing in, it's flowing out, but it's also changing it and changing into another species maybe. And therefore we also need a term that accounts for this reaction influence, and this is IR, like that in example. And then the third class of balance equations is the energy balance. And again, here we have the same story. We have to ask ourselves, okay, we have the storage on the E. It's the energy that is changing in dependency of what goes in over this boundary here into my balance volume. This is the energy in 1 plus the energy in 2 minus the energy flow out. And then we have also the influence this jacket has. So we have a heat transfer between the reactor room and the jacket. This would be plus Q dot. And we have an work that is done on the system or by the system. So we have like changing level. That would mean I'm doing work on the environment. Or we also have the styrer, which is styring and can put in some energy into the system. Quite often these are neglected, these influences. But in the end you have to know that these influences are there and then say, okay, these are so small, I can assume that they are not important. So the next step in our recipe then is to say, okay, we need to talk about transfer rate specifications. And we already talked about one example. We'll see in a second. So this is 4. Transfer rate specifications. And this could be an example mass transfer. So now we assumed before there's no exchange between the gas phase and the liquid phase, but if there would be, we would think about a term that describes this mass transfer. Or we could also talk about energy transfer. And this is something we considered. And an example here is the energy transfer, which is done between the volume and the jacket. So this would then be Q dot. And quite often we say we have kind of a heat transfer coefficient, which is called U. And this is multiplied by the area of exchange, which is dA. And then we have the temperature difference between the both. So it's like the temperature in the reactor, T, minus the temperature in the jacket, which would be an example DJ. And this could then be plugged into this energy balance, and we have already one more step. The next equations we could use are property relations or property specifications. And these property specifications, could be like equations of state, like the ideal gas equation example, or maybe also a thing just simple as that I say, okay, this is a system where we have a dilution, and say we have this an extent so that we can assume our density is just constant. Or we could say we have caloric equations, which are dealing with the energy properties of the system. This is another class, but there are many more you could use here. Then the next class of equations we can use are the so-called balance volume relation specifications. So balance volume relation. And for our example, this would mean, so balance volume specification. For our example, this would mean that the overall volume of the reactor has to relate to the volumes, the balance volumes of both phases. So we could say like the overall V, e.g. overall V of the reactor relates to the V of the liquid phase without a donation or without an indication, and we have the gas volume, we can say is Vg. And then we have one more class of equations, which are the equipment and control constraint specifications. So equipment and control constraint specifications. Good. So equipment and control specifications. And this could be like equipment behavior describing things like a valve equation, or also the behavior of a controller. So we have the equipment constraints and the controller constraints or control constraints. And finally, as you saw, we talked quite a lot while doing this about assumptions. So we assumed there's no transfer. We assumed this is a homogeneous system, it's distributed equally. We assumed the density is constant and so on. And this is a very, very important ingredient of models, because we want to develop models that are suitable for a certain purpose, and they have to be as good and as precise and as usable as necessary, but they also should be as simple as possible. And therefore we have to use assumptions. And this is the last ingredient, modeling assumptions. And we should list them when we are modeling. So it's 8. Assumptions. And these are the, in our example, like the mass of dissolved gas is negligible. Or might be that we have a homogeneous reaction. Or might be we have a solvent in excess. And so on. And these are like the basic ingredients of modeling. And basically, when we talk about these equations, we have two big groups. One are the balance equations, and the other group are the so-called, up to the transfer, constitutive relations. And this is what we need to develop a model. Thanks for watching, and we see each other in the next video.